Then the 8th problem is refrigerant 134A at 1 megapascals 100 degrees is throttled to a pressure of 0.8. Okay, so here this throttling process basically is assumed to be adiabatic throttling. So normally if the heat loss from the throttle valve is not given, we can assume the throttling process to be adiabatic. Determine the specific reversible work and exergy destroyed during this throttling process. Assume the surroundings to be at a temperature of 30 degrees centigrade. Property data are given here. So, the first state 1 megapascals 100 degrees. So, if you go to 1 megapascal table, I see that the saturation temperature is 39.37 degrees centigrade. So, the given temperature is 100 degrees, the state should be superheated vapor. So, state 1 is superheated vapor. So, we go to superheated tables where corresponding to the pressure of this and 100 degrees centigrade, I can retrieve the properties like specific volume, specific internal energy, specific enthalpy, etc. Okay, now let us go and solve this problem. P1 equal to 1 megapascals, which is equal to 1000 kilopascals. T1 equal to 100 degrees centigrade. We have just seen that this is a superheated vapor state. P2 equal to 800 kilopascals. Only one property is there, so I cannot straight away fix the state, and the ambient temperature is given as 30 degrees centigrade. So, now let us fix the take the values. Okay, state 1 is superheated vapor. So, that means I will say I will take from the superheated table corresponding to 1000 kilopascals and 100 degrees. H1 can be retrieved as 335.1 kilojoule per kg. If you go up, you will see that the tables, this is the value for temperature of 100 degrees and 1 megapascal or 1000 kilopascals, corresponding H value is 335.1 kilojoule per kg. Now, again we will also take the value of S1 from the tables, so that we have to do the, so here 1.103 kilojoule per kg Kelvin. So, that is the S1 value. Now, adiabatic throttling. So, heat loss information is not given, and it is customary that throttling process can be assumed as adiabatic. So, Q dot is 0. There is no other form of work involved in the throttling process, so that is also 0. So, that will be equal to m dot into H2 minus H1 implies H2 equal to H1. So, adiabatic throttling process from the first law, it is an isenthalpic process. So, I will say H2 will be equal to H1 equal to 335.1 kilojoule per kg. Okay, so now you can see that from the, so one of the properties is got, another property is pressure, which is given as 800 kilopascals in the problem. So, two properties are enough to fix the state 2. So, what is state 2? You have to go to the tables again. Here, for pressure of 800 kilopascals, the H value is 321 at 90 degrees and it is 337.3 at 100 degrees for same pressure of 800 kilopascals. Again, you can see that we are referring to the superheated tables because the state is superheated. you can see that the Hg value, so H2 value is 335.1, 800 kilopascals, Hg value will be lower than this, so state 2 is superheated. So, in order to get the values, I go to superheated table, I find that the for superheated table corresponding to 800 kilopascals, the value of 335.1. So, actually H2 was calculated of 335.1. So, that is this value, correct. So, now that lies between the temperatures of 90 degrees and 100 degrees, and we have to interpolate linearly to get this. Okay. So, Hg at 800 kilopascals is less than H2, implies state 2 is superheated. Just to record how we found that. Now, what is the temperature? So, we can see from the tables, we can see from superheated table corresponding to 800 kilopascals. Okay, for 90 degrees H equal to for 90 degrees H equal to, we'll go back and see the value, 321.1 kilojoule per kg, and for 100 degrees H equal to 337.3 kilojoule per kg. Okay, so we have seen that we taken from the tables. Now, for the value of H2 equal to 335.1, interpolating for whatever value we want, we get T2 equal to 97.8, it is between 90 and 100 degrees centigrade, and S2 equal to 1.119 kilojoule per kg Kelvin. Okay, so you can see that I am interpolating these two tables and getting the values of T2 and S2. Okay, now I can apply the formula. Reversible work will be equal to the specific reversible work, we can say W reversible is written like this. So, which is nothing but H1 minus H2 minus T naught times S1 minus S2. Do you understand? So, that is the value here, but when you substitute this value, I get 4.85 kilojoule per kg. Okay, now Sgen equal to S2 minus S1 minus Q by T. This is again small Sgen, that is the specific rate of entropy generation, a specific entropy generation, that will be equal to 0.016 kilojoule per kg Kelvin. Now, what is Exergy destroyed? That will be equal to 303 into 0.016, which is equal to 4.85 kilojoule per kg. Is it clear? So we can find in both the ways like this. So here this is 0. So I can say 0 minus, again Exergy destroyed. So that's what we are trying to get here. Okay. So In both ways you can find the Exergy destroyed, this and this. Okay, but you have to understand that the entire process of throttling itself is a irreversible process. When you draw the diagram also, we will find that, see here in a TS diagram, let us say, so this is 1 megapascal and say certain temperature. What was the temperature here? 100 degrees. So this is state 1 and state 2 is, sorry, not this, one second. Yeah, throttling here 1 megapascal to 100 degrees centigrade. So here this is a 1 megapascal, 100 degrees centigrade, a superheated vapor, and the throttling occurs to here 800 kilopascals, again superheated state. The temperature has gone down to 97.8 something. So this is 800. I am just exaggerating the figure. So here this is one. So this process is state 2 and this is state 1, and this process is actually a reversible process shown by dotted dashed line. So you can see that the Exergy destroyed is written in this. So either if you calculate reversible work and do, you can, that will come out to Exergy destroyed only, because there is no useful work from this. Okay, so the Exergy destroyed alone comes out as the reversible work. That is the change in the Exergy. If you directly calculate using SGen also, we get the value. So this is about this problem where adiabatic throttling is assumed. Ninth problem, steam enters an adiabatic turbine at 6 megapascals, 600 degrees centigrade and velocity of 80 meter per second, and it leaves at 50 kilopascals, 100 degrees with a velocity of 140 meter per second. Since the velocity is given, it is implied that the kinetic energy change has to be included. Power output of the turbine is also given as 5 megawatts. To determine the reversible power output, second law efficiency, assuming that the surroundings are at 25 degrees centigrade. So potential energy change can be neglected. So P1 equal to 10 megapascals, T1 equal to 600 degrees centigrade, V1 equal to 80 meter per second. So this is 6 megapascals, 600. Okay, 6 megapascals 600 and V1 equal to 80. Similarly, P2 equal to 50 kilopascals and T2 equal to 100 degrees centigrade, V2 equal to 140 meter per second, and the power developed by the turbine is 5 megawatts. These are the given data. So now let us go to the tables and find this, fix the state 6 megapascals, 600 degrees centigrade. Here 6 megapascals, 60 bar, the temperature is 275.6, but the given temperature is 600, so state is superheated. So go to the superheated tables corresponding to the pressure of 60 bar and 600 degrees centigrade. So this is the state now. So here retrieve the values of enthalpy as 3658 and the entropy as 7.168. So state 1 is superheated, we can find that. So H1 3658 kilojoule per kg and S1 equal to 7.168 kilojoule per kg Kelvin. Similarly, go to the table for 50 kilopascals to fix the state 2. So 50 kilopascals, here temperature is 81.33, but given temperature is 100. So that means you can see that this state also is superheated state. So this is the case where for 100.5 bar you get the state 2 enthalpy as 2683 and entropy as 7.695. So let us give these values. So here superheated state 2. So H2 again is equal to 2683 kilojoule per kg and S2 is equal to 7.695 kilojoule per kg Kelvin. So these are the values. So both the states are fixed. Now first law, Q dot adiabatic, so 0 minus Wt which is given equal to m dot into H1 plus V1 square by 2 minus H2 minus H1 plus V1 square by 2. So that is the thing. So when you apply this, you will get basically everything is known here. Mass flow rate is not known. So enthalpy value H2, H1 are known, V2, V1 are known. So substituting, I get minus, instead of megawatts, I put in kilowatts, 5000 kilowatts equal to, this is positive, so I am putting positive, mass into, I say 2683 plus V2 is 140 square by 2000. Please understand that this is in kilojoule per kg, so I have to put 2000 here, divided by 1000 because 140 square by 2 is in kilowatts per kg, kilojoule per kg, joule per kg, by dividing by 1000 I convert into kilojoule per kg, or else units will not match, minus here this is 3658 plus 80 square by 2000. So this implies the mass flow rate of the steam is equal to 5.163 kg per second, 5.163. Now reversible work can be calculated as m dot into H1 plus V1 square by 2 minus H2 plus V2 square by 2, okay, then minus m dot into T naught into S1 minus S2. Okay, so this is the value. So please understand that we will write H1 minus H2 minus T naught into S1 minus S2, but since I am adding the kinetic energies also, we have to split this into this expression. So now substituting the values, all the values are known to me. Substituting, I will get this reverse work power as, so this is the reversible work. Okay, so now you can see that it is more than the, that is 5.8 megawatts is more than 5 megawatts. So we can calculate the second law efficiency straight away, which is nothing but Wt, the actual work done by the, developed by the turbine divided by the reversible power, which is equal to 5000 divided by 5810.68, which is equal to 86%. The second law efficiency is 86%. Okay, so the work is lost due to the irreversibility. So please understand that here kinetic energy, however small it is included in the problem. Potential energy change is neglected. Then when you calculate the reversible work, it is actually Xi1 minus Xi2, but here the change in the kinetic energy is also included in this calculation also. So basically you get a reversible work which is more than the actual work output of the, this, which is nothing but 5000. So second law efficiency comes out as 86%.